So now we're going to enter a discussion about acid-base titrations. We are going to determine pH of these solutions during the course of a titration taking place. Okay? In this lesson, we're going to focus on the strong acid, strong base scenario. Back in General Chemistry 1, you learned how to take a neutralization reaction, and if you were given a known concentration and volume of one of the things, you could calculate the molarity of the other thing. So we learned how to do titration problems. If you've taken the chemistry lab, you've practiced doing that quite some time. Okay? Might be worthwhile to review that, and we'll do a review problem of it at the very end, I think, of this lesson. Or this series of lessons. All right, so that's what we've done in the past. So here's what we're doing here. We're going to calculate the pH as the course of the titration takes place. These are the possible scenarios that you're going to see. We'll start in this lesson with the first one, strong acid, strong base titrations. Then we will make one of them weak. Either the acid will be weak or the base will be weak. What you will never have to do for us is where both the acid and the base are weak. There becomes too many equilibria for us to worry about and train you in, okay? We'll always keep one of them being strong. It simplifies it. Believe me, it simplifies it significantly. All right, so both of them are strong. What happens when a strong acid and a strong base reacts? Okay, we're going to write a reaction here, not the net ionic yet. I'm going to take a strong acid, and I like HCl, so I'm going to take HCl. And it's a solution that's in water. And I'm going to take some sodium hydroxide. Okay, now we learned that an acid plus a base gives you salt. The cation and the anion come together, and in this case it's actually table salt, okay? Doesn't always have to be that salt, plus water. Okay? By the way, this is the definition of a salt. It is an ionic compound formed by the neutralization reaction. Okay? We've used that word salt a lot. That's what it means. Now, that is an acid-base reaction where both of them are strong. The spectator ions will get in the way. So let us consider what the net ionic equation would be. We know the HCl is actually H plus and Cl minus. The sodium hydroxide is actually Na plus and OH minus because they're strong. They're in solution this way. And this is an ionic compound, so we have Na plus, we have Cl minus. This is the only one that's not broken apart. So we can cancel out all of the things that appear exactly the same on both sides, and we have a net ionic equation of this. Now, the other way you can write this net ionic equation, and I will actually write it this way more often, because H plus doesn't just hang out by itself, it actually attaches to a water molecule, and so I will generally write this reaction this way instead, because of the fact that I always write my strong acids as H3O plus, not as H plus. It is a minor thing, and you can choose to do that. That's fine. I will stay consistent and always write my strong acid as H3O plus. Okay? All right, so this is a one-way reaction because they're strong. They force it to completion. As a one-way reaction, we are able to do ICF tables with this reaction and do calculations with it. So we're going to, before we do calculations, we're going to examine kind of this reaction on the molecular level and monitor how the pH changes during the course of it. So let me go over to the screen here where I can talk about it and write on the screen, and you all can see it kind of blown up. Here is my flask. I have down here in this flask a 25 milliliters of a 0.1 molar HCl solution. Okay? So floating around here are H3O plus ions, right? And up here in the burette, I have sodium hydroxide. I've got the same concentration of sodium hydroxide as I have HCl. All right? Now, this is the reaction, or I don't know why I have it written that way, other than that's how it was constructed and I stuck with it. This is the reaction, right? Same reaction. It doesn't matter which way you want to think about it. Now let's consider the very beginning of this reaction. What we're doing in this graph is we're monitoring the pH in here, okay, as this reaction takes place. Where is it starting? Well, this is a 0.1 molar solution. The negative log of 0.1 is 1, and you see that red dot? That is before I've added any sodium hydroxide at all. And so it's going to have a pH of 1. Now we start adding some. We open up this stopcock here and we start adding some sodium hydroxide. Now we haven't added enough to react with all the acid, but we have added some. So what happens, I add a little bit, what's happening inside of the flask? Well, the amount of H3O plus in the flask is going down. H3O plus's concentration is decreasing because along comes the OH and it is turning it into water molecules. So that is going down, and it goes down a little bit, or the concentration is going down, which is causing the pH to rise. As the H3O plus is going down, the pH is going up, but it's still acidic. I still have acid in there, so I still have an acidic pH. I start getting close to the point where I have added just enough sodium hydroxide to neutralize all the acid, and then when I hit the next dot right here, that's the point at which I have neutralized it all. That is what's happening right here, okay? So that dot and what's in my flask right now are matching. I have just converted all of, how many did I have? I had 1, 2, 3, 4, 5 H3O plus ions. I have now got those things being converted to 1, 2, 3, 4, 5 water molecules. So at this point, I know that I've just neutralized it. Now what's going to happen if I add some more? If I put a little bit more in there, is there any acid to dilute that or to neutralize that? No, I have just used up all of my acid in the flask. But let's not go there yet, okay? What we are at this point right now is what's called the equivalence point. The equivalence point is where the number of moles of your acid and your number of moles of base are stoichiometrically equivalent. Okay, so let's neaten it up a little bit. We're at the point where we have added just as much base as we had acid, and that's called the equivalence point. When the acid is strong and the base is strong, what have we produced at the equivalence point? Water. And what is the pH at the equivalence point? It's 7. And that will always be the case. At the equivalence point, the pH will be 7 if you're titrating a strong acid and a strong base together. All right, so now we're going to go and continue on. We're going to add a little bit more base. So we were neutral, we're at a pH of 7, and we dump in, open up that stopcock and jump in a little bit more base, and it has nothing to neutralize with it. What's going to happen? Well, if that base has got nothing to be neutralized by, it's just going to shoot up. So we're going to have a pH that goes up and steadily rises as we add more and more base to that solution. This is called a titration curve. Okay? This is a very typical titration curve. When they're strong like this, your starting point might be a different starting point. It might be a little lower. If it was a more concentrated acid, instead of 0.1, maybe it's 0.5, it'd be a little bit lower. It might be a little bit higher if it were a more dilute acid, but it's going to be down here. You're going to see it rise. This will never change. It'll always be at 7, and then it'll shoot up to some value past that point. So, procedures for calculating titration, acid-base titrations. It's going to start off looking a little bit like our buffer solutions when we add an acid and add a base. Okay? We've got to write the one-way reaction between the acid and the base. We're going to, since it's one way, fill in an ICF table. We're going to see that F line, and this is where it gets complicated. There are 3 possibilities of what you have. Okay? You are either in a place where you've got conjugate acid-base pairs and you've got a buffer. Now this, notice here, this does not occur when they're both strong. We won't see this, okay? I will teach you about that in our next lesson. There may be only a weak acid or a weak base left in there, and if that's the case, we're going to have to do an ICE table. Again, this does not occur when they're both strong, so I will show you that later. But I wanted to have all the pieces together in one slide for you. If there remains some strong acid or base, you're going to calculate the pH directly from that strong thing. This does very often happen here because we're titrating between a strong acid and a strong base. Okay? So anytime you've got something dealing with weak acid-base pairs, or just a weak acid or weak base, that's when one of them was weak, not when both of them are strong. All right, so we can calculate that pH. We're going to do several here. Okay, we're going to work through several of them. Okay, we're going to do this one here, and we have my reaction all set up here. I want to know what the pH is after the addition of 5 milliliters of 0.1 molar sodium hydroxide and 25 milliliters of 0.1 molar HCl. Okay, so that's this reaction. Here's my net ionic equation. This is an ICF table, and you must plug moles into an ICF table. So we need to know the moles of each of these guys. So let's start with the mole of H3O+. This is from my HCl. Okay, that's the source of my H3O+. So I look over here with my HCl, and I have 0.1 molar HCl. So that's 0.1 moles per liter. I'll call it H3O+. They're the same thing. Oh, times. Okay, we got to get rid of the liters. So we've got a volume of HCl, 25 milliliters. That's 0.025 liters, and that's going to give me 0.0025 moles. And I will put that right here. Now I'm ready to come to my OH. The moles of OH are coming from the moles of NaOH. Okay? I look over here and I see that the molarity of NaOH was 0.1 again. And the volume of that solution was 5 milliliters. So 0.005 liters. Okay, that's 5 milliliters. That's going to give me 0.0005 moles. And I can plug that in here. I don't care about the water. There's a lot of water there. Okay, we don't worry about that number. Now, we look at these two, and ICF goes to completion, consuming the smaller value, which is the base. So I will consume 0.005. I could add it over here, but I don't really care about that number. Now, when I subtract, I have 0.002, and I have consumed all of that added base. So now it says I'm supposed to calculate the pH of this solution. Well, pH, this is not a buffer, so I'm not going to use the Henderson-Hasselbalch equation. All I need is the negative log of the H3O+ concentration. Is that what this is? No, this is moles. We need molarity. Molarity is moles, so I need that number, 0.0020, divided by volume in liters. Well, I had 25 milliliters of the acid. I had 5 milliliters of the base. That's 30 milliliters, or 0.03 liters of the solution, because I want to know the solution in that container after they've mixed together and reacted, and so that's the total volume in there. And what would you expect the pH to be? Greater than 7, equal to 7, or less than 7? Well, it's an acid. All right, we've got acid in here, so I would expect it to be less than 7, and it is. It's 1.18 is the pH. All right, so that is where we're actually, if we go back to our original picture here, go way back, okay, that was early in this solution, right, where we had a lot of acid, a lot of acid. We've just added a little bit of base, so we're down at a low pH still. It's risen up a little bit above 1, but not a lot above 1 at the point where I've only added 5 milliliters of the base. All right, so moving back forward, we are going to do the next one after I erase my board. Okay, so we're looking at this problem. This is a little bit further along in the titration. We're at the point where we have the same amount of both the acid and the base. I'm going to rewrite my reaction that I had up earlier. The strong acid reacts with the strong base, one-way reaction to make our water. Now, it may be possible that when you look at this, you're like, well, the molarities are both the same. The volumes are both the same, so their moles must be both the same, and by definition, that's equivalence point. And at the equivalence point, what's the pH of a titration if they're both strong? It's 7, okay? The pH is going to be 7. So it may be that you don't have to do a thing to recognize that this is at the equivalence point, and that would be my hope. But let's say it's not, you're not there yet. That's okay. I see not E, but F, okay? Let's go ahead and plug in what we know. Molarity and volume, we already calculated that for the acid, and we found that it was 0.02, I think I need another O. I do need another O. Let's get it in there, all right? That's what this was. And then if we take the molarity and the volume of the base, okay, so for the OH minus, the molarity and the volume gives me that same exact number. Okay, so maybe at this point you'll recognize, oh, that means I'm at the equivalence point and I have a pH of 7 because they're both strong. But still you might not recognize it, so you keep on working, and you know that you're going to subtract the smaller of the two. Okay? And then you have zeros, and you might scratch your head and say, now what do I do? Because I'm supposed to take the negative log of something. No, you're going to have to look at that and say, oh, all I have is water? Oh yeah, that has a pH of 7. So at some point you're going to have to recognize that you're at the equivalence point and that your pH is 7 when you have that scenario of a strong acid and a strong base. So now let's go to the next, no, I'm going to have you all do this one, okay? You're going to try it, but I'm going to get you started, okay? So we have our same old reaction. It's a strong acid, it's a strong base, they're reacting. It's a one-way reaction, and we know we need to put moles into an ICF table, okay? Now, we had this, that's never been different, okay? It's the same molarity and volume of the strong acid. But now we have the sodium hydroxide, okay? And our sodium hydroxide, we've put a little bit more in. We've passed up this equivalence point. So let's get the moles of hydroxide. That would be the molarity, which hasn't changed, times the volume, which has changed. It's now 30 milliliters, okay? And so that's going to give me 0.0030, and that's what I'm going to put here, and the water, okay? So you're going to do some work, and you are going to determine which one of those is going to be the pH of this solution at this point. Well, did you get 11.96? If you did, great. If you didn't, I'm going to walk you through making sure you've got it. Those of you who got it, you can check your work and say, yeah, that made sense. Now right here, I could eliminate 2 very rapidly. I know I'm going to have excess hydroxide. It will have to be above 7. If I didn't recognize it then, when I do this, which is to subtract the smaller one of the 2, I've consumed all the acid, and I have some moles of the base. So that's what I can eliminate, and so I've got a basic solution. It has to have a pH above 7, no doubt about it. So I would eliminate the 2 and the 4 right away, and that leaves me with the, the 1 and the 4. Let's say it this way. It'll eliminate the 2.04 and the 5.54, okay? And leave me with the 2 middle ones. Now, we know that this is the OH concentration. So I could get the POH first by taking the negative log of the concentration of hydroxide. This is not the concentration. This is moles. So those of you who took the negative log of 0.0005, you might have got the wrong answer because you took the negative log of a mole instead of a molarity. We need the moles divided by the volume. Well, I had 30 milliliters of the one and 25 milliliters of the other. That's 55 milliliters, or 0.055 liters. And let's see if I had the right numbers over there. Yes, I did. This is going to give me a POH of 2.04. Well, that's a POH. So if you picked 2.04, you weren't realizing it was a POH. pH is going to be 14 minus that number, and that's where we finally get the 11.96. So now we've done an example of the pH before the equivalence point, at the equivalence point, and once you've passed up the equivalence point. So that's when they're both strong. And you'll note when you go through the procedures that we're going to follow, there was a lot of them we didn't have to worry about because we weren't in a world where there's weaks. As we go to our next lesson, we really need to watch it rested, and so that you can really focus on all of those other nuances that we see from the titration.